Hello everyone, my name is Louis Zhou. I work in Johannes Kepler University Linz, Austria, in the chair for Sustainable Transport Logistics 4.0. Today I'm going to present to you our paper, Study of Road-Based Autonomous Vehicle in Snow-Covered Roads by means of behavior cloning using 3D AutoSim. First of all, here is the outline of the presentation. It includes the motivation and then the introduction, in which I will introduce some background and structure of our work. Next is the implementation. In this part, I will roughly explain how we implement the simulation environment. After that, I will explain the experiments that we performed. Then I will demonstrate the results along with some explanation of them. The last part are the conclusion and future work. So first, I'm going to talk about our motivation. The main motivation here is that we want to perform some study of autonomous vehicles on snow-covered roads. And for this kind of study, we need a driving simulator with a very realistic simulation environment. We already have a very good simulator based on Unity 5 named 3D AutoSim, so we want to extend it to be able to simulate the snowy environment and to be capable of road-based machine learning applications. Then, to test the performance of all the newly implemented features, we want to design some simple experiments based on behavior cloning, because we also want to involve human drivers, make a full use of our simulator's potential, since we have a driving kit hardware in our simulator. Okay, the picture on the bottom, as you can see, is a demonstration of our simulator. Above is the basic architecture of the whole simulator. ROS is connected with Unity via ROS Bridge, which is a package that manages the data exchange between ROS and any platform outside ROS. We also aid a neural network on the ROS side via ROS Python API, so that we could enable the machine learning capabilities. And here is a high-level overview of the overall architecture of the behavior cloning applications. It is basically the same as the architecture I showed before, just with more details. As you can see from the 3D AutoSim side, we are using real human drivers for data collection. We collect the steer angles of the real driver and send them to the ROS side, along with the corresponding camera images that we get from inside the Unity simulation. Then we do some pre-processing, such as rescaling, and use them for training. The steer angles are the ground truths of the output. And later during the test or experiment, we again feed the camera images to the neural network and eventually transmit the output of the neural network, which are also steer angles back to the Unity for control of the vehicle. Okay. To the implementation of the environment, since this part is mainly about 3D game graphics, I don't want to go too deep, so I will directly show the final effect and briefly introduce how we achieve it. First is the effect of snow falling, as you can see from the picture here. This effect is also very common in other driving simulator. In this work, it was achieved through the Unity's particle system, which allows 2D or 3D models to be released as particles within range with certain rules and density. Next is the effect of snow covering the road. As can be seen from the image, there are several car tracks on the snow cover part. And this effect could be pretty important and interesting for the visual-based machine learning approaches. To achieve this effect, we first apply a plane to the corresponding wet textures and the normal map to resemble its appearance to a snow ground. We then performed the tessellation process on the mesh of the plane to increase the triangles on the mesh, and this technique makes it possible to better replicate the snow ground plane to simulate the effect of the depression after snow was compressed, as well as the folds of the snow. And next, we use a camera and the corresponding render texture, which could be considered as a format of image, actually, to record the path of the four wheels on the snow plane. And finally, we developed and executed a script to make the meshes where wheels pass on the snow plane to sink down to form car tracks. And finally, we cover the entire road with plane like this. And for the less important part, we simply use white textures to aid some snowy atmosphere. To evaluate the newly implemented simulation, we designed a series of experiments. First, we invited several drivers to participate in the creation of dataset. The drivers were required to drive as safely as possible and try their best to stay in the lane. Here is the neural networks we used. It is very simple. It takes an RGB image as input and eventually output a float number, which is the steer angle. And the road was initially fully covered with snow, and the car tracks of each lap of driving were kept during the data collection, and therefore they were also captured by the front camera of the car. And as explained earlier, we only use video recordings and the steer angles for training. After the training phase was completed, we used the model to perform the experiments and compare the results of different situations. The first experiment was conducted with the road completely covered with snow, so without any car tracks. And the vehicle speed was set to 50 kilometers per hour constantly. With this relatively low speed, although the lane could not be seen, the vehicle could still be stabilized in the correct lane range. This image here shows the car tracks left on the snow after a vehicle have driven several laps autonomously. The car trajectory overlapped almost completely with the previous track. And then a second experiment was carried out in which a lot of car tracks were added in advance to simulate more complex snow road conditions. And this image shows that the vehicles could still maintain a center position on the lane. And next, the experiment was performed at a higher speed of 100 kilometers per hour. The results showed that the vehicle could stay in the correct lane range most of the time. However, when turning at a large angle, as can be seen from the image, the trajectory of the vehicle shifted significantly. And since we didn't include the acceleration and brake input in the training, this behavior is actually reasonable. And in order to verify that the model could output an accurate steer angle under a real-time controllable speed, we involved the real drivers again to drive cooperatively with the trained model. And this time the drivers were required to only control the acceleration and brake without steering. And then the result is getting better. I will show the comparison of the result later. And to verify that the model did not completely ignore the road surface features, we also tried to remove the snow plane. And in this case, the model could no longer give a reasonable output. Since we only trained it under snowy environment, this was expected. And this table shows the comparison of the lateral deviation from the center of the lane in the 4 experiments. As can be seen from the 2 low-speed tests, they have the same result. And with higher constant speed, the deviation increased a lot. And with human control speed, the performance got better. And since the width of the lane is about 3.5 meters, and the virtual vehicle model used in the experiment is about 1.73 meters wide, we could see that the vehicle could maintain the lane under low speed and semi-auto conditions. Here are some more visually intuitive representations. On the left are the trajectories recorded from the first 2 tests. As can be seen, they overlapped perfectly. On the right side is the comparison of the deviation of each test to the center of the lane. And as can be seen that the green line, which is the higher speed test, has the biggest deviation. Then it is the conclusion. In this work, we extend the 3D co-auto-sim simulation platform with realistic snow simulation. Behavior cloning was used to assess the approach. By carrying out multiple experiments in different snow environments and analyzing the impact on the performance of the newly implemented models, we showed that a single visual input model makes it possible for the vehicle to maintain its position in lane and the different kind of snow conditions. And the car track features promoted the learning and generalization steps in the machine learning process, and therefore conclude that the proposed approach is appropriate to develop simulations of snowy conditions. In future work, more complex scenarios such as more diverse surroundings, other vehicles, etc., will also be added to the system, and we also want to enable the reinforcement learning capabilities for the study of more complex situations. Thank you very much for your attention, and keep safe and healthy.